Hello everyone, I'm Panrong from Nanyang Technological University. I'm delighted to introduce our work, Large-Scale Vehicle Trajectory Reconstruction with Camera Sensing Network. This is a joint work of NTU and Alibaba Group. Vehicle trajectories compared with origin-destination pairs provide more complete information for individual communities and the underlying city. Accordingly, a trajectory dataset of not only participating vehicles but also of general vehicles can more truthfully reflect human mobility, therefore supporting more accurate decision-making in applications like intelligent transportation system, traffic analysis, and urban planning. However, existing vehicle sensing solutions fail to build accurate and complete trajectory of all vehicles. They either track in-vehicle devices, get only partial knowledge from participating vehicles, or monitor roadway with flow sensors, capture only anonymized traffic flows. In this work, we propose VTrack, a system that employs traffic cameras as a sensing network to observe general vehicle movements and reconstruct their trajectories on a large scale. Using traffic cameras has two main advantages. First, they are usually widely deployed in cities. We investigate an urban area in China and find out over 1,000 traffic cameras covering nearly 60% of the intersections in that area. Those cameras constantly take low-resolution videos and produce about 7 million vehicle snapshots each day. Such a high coverage provides an opportunity for sensing complete vehicle trajectories. The second advantage is that camera observations preserve identity information for general vehicles. As a vehicle moves around the city, it could be captured by some traffic cameras with locations and timestamps. If we can estimate vehicle identities from captured snapshots and maintain a consistent identity estimation across all cameras, we can then reconstruct all the trajectories. However, there are two key challenges in designing the VTrack system. The first one is identity uncertainty. Traffic cameras are purposed for observation and constantly take low-resolution videos. From these videos, the license plate image is often small and subject to various imperfections. It is challenging to accurately recognize all the plate characters, even for state-of-the-art DNNs. The second challenge is identity consistency. Trajectory reconstruction requires a consistent identity assignment to snapshot by different cameras. However, maintaining such consistency is challenging, as snapshots by different cameras are under different environmental conditions and are of very different quality. As a result, one vehicle may look different on different cameras, while different vehicles may have similar appearance, especially those from one manufacturer. This brings ambiguity when inferring trajectories. Let's look into the first challenge regarding identity uncertainty. As mentioned, license plate recognition errors result in high uncertainty when inferring trajectories. The figure shows a typical example. Record 3's plate at camera C is wrongly recognized, which leads to uncertain roads from camera A to B. We analyzed the LPR result of over 2,000 snapshots and found that over 90% of them contain errors, but mostly with only one or two characters wrong. Besides plate, visual appearance is another useful clue to identify vehicles. However, if we apply vehicle re-ID with only visual features, 5 snapshots of other identity rank top together with record 3. The inclusion of them will severely divert the trajectory. Therefore, purely relying on appearance features may incur too many false positives. To reduce the identity uncertainty, we propose a multi-dimensional similarity block, shorted as MDS block. For any pair of vehicle snapshots, the MDS block derives a more robust identity similarity measure, which gains combined confidence from 3 aspects, namely plate similarity, appearance similarity, and mobility similarity. Specifically, for plate similarity, VTrack employs a CRN model to recognize only readable characters on plate images. With that, VTrack is able to handle plate that contains unreadable characters or have varied lengths. The plate similarity between plate A and plate B is modeled by their added distance. For appearance similarity, we focus on the three most intrinsic attributes: color, type, and brand, because these attributes are generally available and relatively robust across snapshots taken by different cameras at different environmental conditions. Appearance features are extracted by a multi-head resonant model whose cosine distance is modeled as the appearance similarity. Apart from visual clues, VTRAC models the mobility similarity by the probability that a vehicle can travel from one location to the other within the time constraint. An inverse Gaussian model is employed to model the travel time difference between historical routes and the target snapshot pairs. Finally, the MDS block combines the three estimator with a product and outputs a MDS score describing the probability of two snapshots having the same identity. That was the first challenge and our solution to reduce the identity uncertainty. Let's move to the second challenge, identity consistency. As mentioned, the key problem is how to assign vehicle identities to snapshots for assembling trajectories. Query-based approaches have been conventionally applied to this problem, where pairwise distances from a given query snapshot to others are evaluated, and those within a predefined threshold are considered the same identity as the query. However, the figure shows query-based conventions suffer from identity inconsistency. When querying with different snapshots of vehicle A, it may give different identity assignments. Worse, query-based approaches provide no guarantee that all closed snapshots are of the same identity, and the best threshold may differ from query to query. As a result, it fails a number of hard cases. VTRAC ensures identity consistency by modeling complex relations among all snapshots with a graph structure. Unlike query-based approaches, a graph can model system-wide relations to achieve global optimal in identity assignment. The hard cases that fail pairwise assessment may get inferred from their correlations with other strongly connected pairs. This figure gives an overview of VTRAC's workflow. On the upper layer, VTRAC learns a consistent identity representation for each snapshot. It first builds a snapshot graph to capture system-wide correlations, where vertices represent all the snapshots and the edges denote the MDS scores. VTRAC reduces the number of edges by removing those of large spatial temporal spans. As a result, the snapshot graph is sparse, which ensures the computational efficiency of later processing. To get consistent identity representation, graph convolution is performed, where each vertex keeps updating itself with the knowledge it gains from its neighboring vertices. In this way, the system-wide correlations are encoded into vertex representations. As a result, the representations of snapshots from the same trajectory tend to agree, while those from different trajectories tend to differ. We can thus cluster snapshots into individual trajectories by the learned representations. Since the representations are sparse, VTRAC first employs the random projection to reduce the dimensionality and then performs HDB scan to cluster the learned representations into trajectories. On the lower layer, VTRAC inspects trajectory-level mobility on road networks for further accuracy. An iterative self-training process is introduced, which models the trajectory feasibility by transition probability on a road network graph built from maps. It then detects positive snapshot pairs from feasible trajectories and negative snapshot pairs from infeasible ones. By feeding those pairs back to the GCN, the self-training enhances the GCN by incorporating trajectory-level mobility into the representation learning process, and thus improves the overall accuracy. For evaluation, we present VTRAC's performance on an urban scenario with a complex road network. In total, we obtained over 1 million snapshots from over 1,000 cameras in morning rush hours. We manually labeled two representative sets of ground truths. One contains 125 public transit trajectories, and the other contains 300 private vehicle trajectories. To the best of our knowledge, none of the existing work can directly reconstruct trajectories of general vehicles from camera snapshot. We thus borrow key ideas from three different principles and implement them for reconstructing trajectories. LPR scheme represent common practice, where we record snapshot by plate and form trajectories by linking consecutive snapshots with the shortest path on the road network. ReID scheme represent vision-based method. Considering the high false positive rate of using only vision features, we adopt a progressive vehicle ReID pipeline, where we first employ a cross-filter with visual features to select candidates, which are then refined by plate and mobility information. Our most likely trajectory is formed by the shortest path on the road network. Finally, HRIS scheme represent mobility-based methods. Instead of using camera data, this scheme assumes that trajectory with the same OD usually have similar road choices, and thus rebuild uncertain parts of the trajectory by referring to the most popular roads sharing the same ODs. The upper figure shows the ground truth trajectory of the three path roads, and the lower figure visualizes the reconstructed result of one trajectory on bus route 1. As shown, VTRAC successfully reconstructs the correct trajectory. The trajectory by LPR deviates from the ground truth in several sub-trajectories due to the loss of snapshot with plate recognition errors. Therefore, the granularity of the reconstructed trajectory is limited. The trajectory by ReID is largely deviated from the ground truth due to the misclassified snapshots. Many false positives that belongs to other vehicles leads to wrong detours and limited the precision of the reconstructed trajectory. The trajectory by HRIS is a very different path compared with the ground truth. That is because most vehicles that share the same OD choose different roads from the bus. We also present the spatial distribution of all the public transit trajectories by VTRAC and alternative schemes. We see that most of the trajectory reconstructed by VTRAC are correct, and they converge to the ground truth routes shown in Figure A. Substantive noises exist in trajectory by LPR and ReID due to the identity uncertainties. The trajectories by HRIS converges to routes of high inaccuracy. Overall, VTRAC is able to correctly reconstruct 89% of the trajectory from both public transit and private vehicles, which outperforms other alternatives by at least 59%. For precision and recall, VTRAC produces trajectories with 94% precision and 91% recall, which outperforms other alternatives as well. LPR cannot handle snapshots with wrongly recognized plates, which result in a fairly low recall. ReID achieves a slight improvement on the recall, but at a cost of largely reduced precision. HRIS gives an accuracy comparable to ReID. To summarize, we present VTRAC, a system that reconstructs vehicle trajectories from low-quality traffic camera data. To tackle the identity uncertainty and inconsistency challenges, we propose a comprehensive system design including MDS, graph convolution-based identity learning, and self-training process. Real-world experiments suggest 89% overall accuracy. Please refer to our paper for more details. Thank you for listening.